Hey everyone, welcome back to Calculus 2. This will be lecture 21. In this lecture we're going to discuss indefinite forms and L'Hopital's rule. Okay, so we're going to take a step back and talk about derivatives here, and we'll need these differentiation techniques for some of the sections that will come. We'll need some of these limit techniques for some of the sections that will come in next week and then the following weeks. So let's jump into it. Now we'll go ahead and call this section 3.7. So this is 3.7 and indeterminate forms and L'Hopital's rule. Okay, so we would have talked about this briefly during the early sections of Calculus 1, this idea of indeterminate forms. But let's recall, what do we mean by an indeterminate form? So recall 0 over 0, infinity over infinity, etc., and we'll talk about what all of them are called indeterminate forms. Okay, mainly because they do not guarantee. So this is all in regards to taking a limit. So whenever you're evaluating a limit and you get a 0 over 0 or infinity over infinity or other such things, we call them indeterminate forms because they do not guarantee that a limit exists, first of all, and if a limit does exist, they don't indicate what the limit is. Right? So these are called indeterminate forms because they do not guarantee that a limit exists or tell you what the limit is if it does exist. Okay, so that's the key word there, indeterminate. Right, so let's consider an example just to kind of refresh our our memory on this. So consider this limit. Limit as x approaches -1 of the function 2x squared minus 2 over x plus 1. Okay. So if we were to use like direct substitution on this, right? Like if you just, these are both polynomials, so you might imagine, hey, I can just plug in a -1. Well, if you try that, direct substitution, you will see that substitution, that produces the indeterminate form of 0 over 0. Right? Because you would get 0 on the bottom and you get 0 up top. And so basically evaluating this in a sort of direct way doesn't really help us. Right? But when we encountered this in Calculus 1, when we were learning limits initially, we would employ sort of algebraic tricks and algebraic maneuvers to still allow us to identify the limit, even though the function may be undefined at the limit point itself. Right? So for example, with this one, we can rewrite this as, we could do a little bit of factoring and cleanup work, and we could see that this is, x approaches -1 of, you can write this as 2 times x squared minus 1 over x plus 1. And then, of course, the x squared minus 1 can be factored down. And you get 2x plus 1, x minus 1, and then that's all over x plus 1. Right, and then that being the case, you can do the cancellation, and you see that this limit is, in fact, 2 times x minus 1, so you would get, what, -4. Okay. Right, so in this case, considering the function on its surface produces an indeterminate result here, but we learned techniques, algebraic techniques, to allow us to still identify the limit, right? Another example of kind of something we've done in the past would be like this guy here. What about this example? The limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. Right? So in this case, direct substitution would produce the indeterminate form of infinity over infinity. Right? And so that being, we know that in fact the limit here is 3 over 2, right? 3 halves. And we would have employed the following technique to evaluate those. We would have said this is equal to, well, this thing here, well, let me just rewrite it. 3x squared minus 1 over 2x squared plus 1. Right, we could have done this nice trick where we divide the top through by x squared and the bottom through by x squared. And so we would get 3 minus 1 over x squared divided by 2 plus 1 over x squared. Right, and then we would have said, okay, this piece will go to 0, this piece will also go to 0, these two will remain, and the limit is 3 halves. Right, so again, another example where we can employ some algebraic techniques to get around the indeterminate form. Now these are all examples of algebraic functions, right? But occasionally we can use this on functions that are transcendental, like for example this one. Consider the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. Okay. So in this case, if x is approaching 0, then basically these terms are going to be zeroed out, and this would produce 0 over 0, right, using direct substitution. Right, but in this case we can kind of do a trick similar to the first example. Right, we can just do some algebra here. And basically we could factor that numerator apart, and you get e to the x minus 1 times e to the x plus 1 over e to the x minus 1, right? And then that, of course, naturally gives us this cancellation. And we can see that the limit here would be, basically 1 plus 1, so 2. Right? So again, it's just kind of another little way to get around the indeterminate form that you observe, via direct substitution. Now, this doesn't always work, however. Hence the need for another section on this. So not all indeterminate forms can be, evaluated by algebraic manipulation like this. So, and this is actually something that comes up a lot when you have expressions that have, singularities, where the expression is, involves both a transcendental and kind of an algebraic part, right? So a good example there would be, kind of a simple example would be this one: limit as x approaches 0 of e to the 2x minus 1 just over x. Right, so in this case, this is going to produce 0 over 0 as written, right? And if there's some rewriting you could try. Maybe you could do something like this. 1 over x. Right, and in this case, what do you get? Well, you get, this is going to be infinity minus infinity, which is another indeterminate form, right? Anytime you're subtracting infinity from infinity, you're looking at it wrong, right? So something like this, though, it is the case that this limit does exist, and it's actually 2, right? So this limit, right? And we could employ numerical methods to establish that limit. We could just evaluate the function ever closer to 2 from both sides and see clearly that the limit exists and that it's 2, right? So sort of empirically go find it. But what we want to do here is we want to have more sort of closed form kind of approach to this, right? And that's where L'Hopital's rule comes in. Okay, so L'Hopital's rule comes into play in situations like this, where you have an expression where the limit exists, but you can't identify it because of indeterminate forms, and there's seemingly no algebraic technique that can be employed to allow you to evaluate it. Okay, so let's go ahead and state L'Hopital's rule. We'll state it's a theorem, and then we'll do examples. Right, so it's a little bit wordy of a setup here, but so this is L'Hopital's rule. So for this, we're going to let f and g be functions. So let f and g be functions that are differentiable. Okay, on an open interval AB. Okay, and this this interval is going to contain C, some value C. So f and g are functions that are differentiable on this open interval AB, which contains C, but they may not be differentiable at C. So I'll write except possibly at C itself. Right, so we've heard this wording before, right? So f and g are functions that are differentiable on this interval AB. C is a value in that interval, and f and g may not be differentiable at C. Okay. All right, so assume that g prime of x is non-zero, right, for all x in AB. And then here we'll say also except possibly at C itself. Okay. All right. Okay, so f and g are functions differentiable on an open interval containing C, except they may not be differentiable at C. And further, assume that the function g, the derivative of that, is non-zero everywhere on the interval except possibly at C. Okay, so this is kind of stuff we've seen already, right? So, all right, and the next thing is then if the limit of f of x over g of x as x approaches C, so if this limit produces an indeterminate form, right? And what do we mean by an indeterminate form? Well, we mean 0 over 0, infinity over infinity, 0 over infinity, infinity over 0. Okay, those are the 4 basic ones. Then here's the punchline, right? So so before we say the punchline, let's make sure we understand this. So f and g are 2 functions differentiable on a suminterval AB, right? The derivative of g is non-zero on that entire interval. Naturally, that's because g is the denominator, right? Then if the limit of the ratio of f to g as x approaches C does produce an indeterminate form, right? So if you have this problem, kind of like we've seen in the previous examples, where you've got f over g, and when you evaluate them, when you evaluate the limit directly, you get an indeterminate form, 0 over 0, infinity over infinity, whatever. If that's the case, then the limit as x approaches C of f of x over g of x will actually be equal to the limit as x approaches C of f prime of x over g prime of x. All right, now what we should say is provided that the limit of f prime of x over g prime of x exists, at C. Or, it is fine to say that it's infinite, right? Right. So if this limit is, infinite, that's fine too. So provided that the limit of the ratio of the derivatives exists at C or is infinite. Okay. All right. Told you it was wordy, right? So it's an in-depth thing, right? But so what it basically means is that, hey, look, if you're dealing with if you have some function that is a ratio like this, which when you try to identify the limit at a particular point C, and direct substitution produces an indeterminate form, then it turns out that you could differentiate the top and the bottom separately, and that whatever the limit is there is equal to the original limit. Okay, so that's kind of interesting, right? So that's interesting. The proof of this is a little bit tricky, so we're not going to go through it, but it is available in most textbooks. You can look at it online. But basically, this allows us to take a function where, hey, we're trying to find the limit of this function at this particular point, but it's eluding us, and there's no algebraic techniques that can be employed. We're sure the limit exists as we can see it numerically, but we just can't quite figure out how to manipulate this expression. Well, this is another tool in the toolbox which would allow you to manipulate the expression in a way that makes it probably more accessible to the to evaluation. All right, so let's do an example. Let's do an example of this and see how this works. Okay, so say I've got say I want to evaluate the limit as x approaches 0 of e to the 2x minus 1 over x. Okay, so you can think of e to the 2x minus 1 as your f, and just x as your g function, right? So first of all, these are both differentiable functions on an interval around 0, no problem. And we can see further that g, the derivative of g, would just be 1, and that derivative is non-zero on any interval. And also, kind of the first thing I guess we should check is that this does produce an indeterminate form when we use direct substitution, right? So e to the 2x when x is 0 is 1. So 1 minus 1 over 0. So 0 over 0. So produces 0 over 0. Okay, so check that part. Both differentiable, right? Check, right? G prime of x non-zero, check. Okay, that's what we need, right? Those are the pieces that we need, and so this means we can use L'Hopital's rule. And so so that means basically that the limit as x approaches 0 of e to the 2x minus 1 over x, that's going to be equal to the limit as x approaches 0 of the derivative ddx of e to the 2x minus 1 divided by ddx of x, right? So I'm being very intentional with all of this notation here. And so we can differentiate these easily. The derivative of e to the 2x minus 1 will just be what? 2 is the chain rule on this front piece here, so there'll be 2e to the 2x. And then down here we just have a 1. Okay, and so we can see clearly that if we, this limit is going to be, this e to the 2x is going to go to basically 1, right? And so this whole thing will be equal to 2. And so this means that the limit here, the initial limit that we were given is equal to 2 as well, right? That's sort of L'Hopital's big theorem there, right? That we can differentiate the top and bottom, and we can find the limit of that new ratio functions, and the limits will be the same as the original function. Okay, now notice a couple things here to be careful of, right? Things to point out here. First of all, notice that in this chain of reasoning here. We don't actually know so we don't actually know that the limit of f over g is equal to the limit of f prime over g prime until we actually find this second limit, right? We don't know that they're equal, right, until we are able to determine that this limit actually exists, right? If this limit doesn't exist, then they may not be equal. This limit may still exist if this one doesn't, right? But if, you know, these criteria are met and this limit exists, then these two are equal. Okay, so we don't actually know that this is true until, you know, we find limit of f prime over g prime. Okay, this is something just to keep in mind. All right, when working through examples. Right, and I mean, you know, a lot of times we take for granted like this equals this equals. I mean, these, you know, this may not be true, right? If this limit doesn't exist, then this is not necessarily true. It's possible for the limit of the ratio of the derivatives to not exist, in which case these two would not be equal. But if this limit does exist, then they are equal, provided that these things are met. Okay, so that's the first thing to note. Note also, you know, secondarily, that when we say f prime of x over g prime of x, you know, this is not, you know, the quotient rule. A lot of times, you know, I've seen this, you know, when teaching this class, you know, people will, you know, they'll see the derivative, they'll see, you know, they'll see f over g like a ratio, you know, a rational function like that, or a ratio of two functions, and they'll assume the quotient rule, right? This is just totally different than the quotient rule, right? The quotient rule is, you know, is this, and that is not the same thing as this. Okay, right? This is simpler than the quotient rule, right? This is literally just take the derivative of f, and this is take the derivative of g. The quotient rule means take the derivative of the ratio of the two, right? Here we're treating them separately. Here we're treating them, you know, together. Okay, so just a little note, common mistake that I see people making when they come across this L'Hopital's rule. All right, let's do another example. Let's say we want to evaluate the limit as x approaches infinity of the natural log of x over x. Okay, so we've got this. Now, if we were to evaluate this directly, of course, this is going to produce infinity over infinity, the indeterminate form, right? We know that these are both differentiable, right? And then g prime of x is non-zero, right? So we can see all of these things just by looking at it, right? So that means we can use L'Hopital's rule, right? So let's try to plug that in and see what happens. So the limit as x goes to infinity of the natural log of x over x, right? So according to L'Hopital's rule, which this should be, if the limit exists, this should be equal to the limit as x approaches infinity of, you know, the derivative of the natural log of x over the derivative of x. Okay, and what do we get here? Well, the derivative of natural log of x is 1 over x. The derivative of x is 1. Okay, so this is going to be equal to the limit as x approaches infinity of 1 over x, right, which of course is 0, right? So x, the denominator, grow without bound, this will be 0. Okay, and so that means because this limit exists and these other conditions are met, then this derivative, or this limit, will have the same value. Okay. Excellent. All right, very good. So these are kind of simpler examples, just sort of getting used to the conditions that we have to check and the things we have to do. Sometimes it can be necessary to, sometimes we'll find examples where we have to apply L'Hopital's rule repeatedly, right? Such as this example. Let's say we want to evaluate the limit as x approaches negative infinity of x squared over e to the negative x. Okay, direct substitution here is going to give us what? Well, if this was negative infinity squared, then it's infinity, and the bottom is e to the infinite power, so it's infinity over infinity, isn't it? Right. So this is going to produce that indeterminate form. Can we differentiate both top and bottom here? Yep. The derivatives exist. And what about the derivative of e to the negative x? Is it non-zero around, as x goes to negative infinity? Yes, it is. G prime of x is non-zero. Okay. Right. So for for values that are heading off to negative infinity, this is going to be e to some insanely large number. So it's definitely non-zero. Okay, so we can use L'Hopital's rule. And let's see what happens here. So x squared over e to the negative x. So we're going to differentiate this. Like so. And what do we get? We get 2x on top, and then down below it's negative e to the negative x. Okay, now what happens here? Well, here we have a problem still, don't we? Right? This guy still produces an indeterminate form. In this case, since it's negative infinity, this will be negative infinity on top, and then down below it would be the same as before, except now you got the negative sign in the front, so now it's negative infinity over negative infinity. Right? So still indeterminate. Right? So what we can say then is this is going to be equal to, in theory, if the limit exists, it'll be equal to the derivative of this again. Right? So the limit as x approaches negative infinity of the derivative again of the top and bottom separately, like this. Right? And so we would get the limit as x approaches negative infinity of 2 over e to the negative x. Okay, now what happens here? Right? Does this look better? It does indeed, right? Because now we have 2, and this denominator is going to grow without bounds, so this is going to give us a nice, determinate form, right? So 0. Right? So this limit exists, and so that implies that this one is equal to this one, and since this one exists, that implies that this one is equal to it. Right? So kind of chain of reasoning going backwards. This existing means this one is equal to 0, and this one having a value of 0 means that this one is now equal to that one. Okay? So kind of reverse. All right, you have to kind of find one that works, and then it sort of means that everything before it kind of falls in line. All right, excellent. All right, let's do some more examples. I think this is powerful just in the straightforward examples, but this can be really powerful when you kind of combine it with a lot of tricky algebra, right? So what about like this example where we want to evaluate the limit as x goes to infinity of e to the negative x times the square root of x. Okay, so in this example, right, this is direct substitution here is going to produce what is it going to produce? Right, this is going to become 0, and this would be infinite. So this is like 0 times infinity. Okay, which strictly speaking isn't an indeterminate form that L'Hopital's rule directly addresses. So L'Hopital's rule does not apply to this form. Okay, but if you just look at this for a second, you can probably easily see how we could maneuver this expression to make it fit something that L'Hopital's, to make it look like something that L'Hopital's rule can address, right? So in particular, we could rewrite this. So instead of e to the negative x times the square root of x, we could write square root of x over e to the x. Right, so just kind of rewriting the expression, what is this going to produce? Well, now you're going to have, you know, this is going to be infinity over infinity, right? Okay, so this is, you know, now this is the indeterminate form that we can use the L'Hopital rule on. Okay, so doing so means we basically differentiate top and bottom, right? So I'm just going to do that. This would be 1 over 2 times the square root of x up top when I differentiate it. And then this bottom would be just the same, right? It's e to the x, the derivative is the same. And so what do we get here? Well, this is the limit as x approaches infinity of what? 1 over 2 e to the x times the square root of x. Okay, and so now this is we can understand what this is telling us, right? So it basically e to the x is going to blow up, square root of x is also going to blow up, so the denominator increases without bound, and so this is going to be 0, right? And so that means that's equal to 0 as well. Okay, now you might have been able to guess this just by kind of looking at these values and say, well, e raised to the x power is going to increase much, much faster than the square root of x, right? But, you know, this kind of shows you without doubt that it's true. Sometimes you can kind of reason about some of these. This is a good example of that. That's a good skill to have, just you know, willingness to kind of look at the functions and say, oh yes, this one we know increases faster than this one. That'll be something that comes up in the coming sections a lot. Kind of thinking about them in that way. And then also as you get further into your math coursework. Let's see. So let's do another example, something a little bit harder, right? Something that's a little trickier. Something that requires a little more trickery, right? So let's say we want to evaluate this limit. So the limit as x goes to infinity of 1 plus 1 over x raised to the x power. Okay, so what happens just looking at this direct substitution, right? This term here is going to go to 0 as x grows, and you're going to end up with 1 raised to the x power, which is kind of like, you know, direct substitution produces 1 to the, you know, kind of an infinite exponent here, right, which is not exactly helpful. But we can kind of get tricky with this one, right? We can use some algebra. Plus L'Hopital to figure this out. Okay, so because one to the infinite, 1 raised to the, you know, power of infinity does not tell us, you know, what this limit is, and it doesn't give us any, you know, or if it even exists. So what we're going to do is we're going to assume that the limit exists. We're going to assume that the limit as x approaches infinity of 1 plus 1 over x to the x power exists, and set it equal to y, right? Some value y. Okay, so basically we're going to say this: y equals this limit. Okay, and then we're going to do some tricks, right? So one of the big problems with this is this exponent here, right? So we can use the properties of natural law of logarithms to deal with this exponent, to rewrite in a different way, right? So if I take the natural log of both sides, like so. Okay, then it's perfectly legal for me to come in here and say, okay, then now I have the natural log of y equals, and I can swap these two. The limit as x approaches, this should be infinity, not y. X approaches infinity of the natural log of 1 plus 1 over x to the x. Okay, and then that being the case, that allows me to bring the exponent down front. That's like a natural, that's like a logarithm technique, or logarithm property of logarithms. All right, so now I have the natural log of y is equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Okay. All right, let me flip pages here. Okay, so just to put this on here, so the natural log of y is equal to the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. That's kind of where we left off. Right, and so then we can do something interesting with this x here. So the next thing, I'm just going to kind of write it like this. So then we can say the limit as x approaches infinity of, now it's natural log of 1 plus 1 over x, and then instead of having the x multiplied, we can divide by 1 over x, right? Like so. Okay, now what happens here is, you know, if you evaluate this directly, you would say, okay, this is 1 plus 1 over x, right? And the natural, so this is all going to 1, which is going to be 0, and this is going to 0 as well. So this produces 0 over 0, which is one of our forms. This is the indeterminate form. So that means we can use L'Hopital's rule. Right? So we've kind of maneuvered this expression so that it produces an indeterminate form. We know that the top and bottom are differentiable and that the bottom is non-zero, the derivative is non-zero. And so this means we can use L'Hopital's rule. Right? So we have the natural log of y is equal to the limit as x approaches infinity of the derivatives here. So d dx of the natural log of 1 plus 1 over x, that's the top, right? Differentiating this right here. And then d dx of 1 over x. Is that part? Okay, perfect. Now kind of off to the side here, what is this derivative? That's a little bit of a little bit tricky. All right, let's see here. So this would be, so note, we'll just write this off to the side. d dx of natural log of 1 plus 1 over x. Now, so you have to use kind of the chain rule, right? So the natural log of this expression is just going to be 1 over that expression. And then the derivative of that inside part, it has to be multiplied by that, right? Like so. So you have 1 over 1 plus 1 over x times this derivative, which is negative 1 over x squared. Okay, so that's just kind of like what this numerator is equal to, is this. All right, and then obviously this one is straightforward to grab. So let's continue. Okay, so that's going to imply that the natural log of y is equal to the limit, just plugging those values in, or those functions. Right, this is going to be the limit of, you know, so it's this part, 1 over 1 plus 1 over x times negative 1 over x squared. And then this derivative here is negative 1 over x squared as well. Right? Okay, so that's good. We can get a nice cancellation here. Okay, so that means the natural log of y is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. Now what is that? Well, x is the only thing, is the only moving part here, right? So that means x is growing without bounds, so this is going to go to 0, right? So this whole thing is equal to 1. I mean, this part here is equal to 1, right? Which obviously implies natural log of y is equal to 1. Okay, now when is that true? When is the natural log of y equal to 1? Well, it's only true in one case, and that case is when y is equal to e, right? So natural log of y equals 1 implies y equals e. Okay, now remember, y is our assumed value of the original limit we were looking at, right? So because we said that y is equal to the limit as x approaches infinity of 1 plus 1 over x to the x power, that's what we said. This is going to imply that this limit, the limit that we were looking at initially, is equal to e. And that's a beauty right there. All right, so e is the limit as this expression grows without bounds. So that's a pretty nice function. Perfect. That was a good example, kind of a fun one. Let's say maybe we'll do one more. What about this one? So the limit as x approaches 0 from the right of sine of x to the x power. Well, this is going to produce, the form 0 raised to the 0 power, all right? Okay, which strictly speaking isn't very helpful. We're going to do the same trick on this as we did previously. We're going to assume the limit exists and set it equal to y. So y equals sine of x. Y equals the limit as x approaches 0 from the right of sine of x to the x power. Okay. And so just like before, let's take the natural log of both sides. And I'm going to do this kind of in one step. It's a two-step thing, but I'm going to move the natural log inside and bring the exponent down, right? So taking the natural log here would be the natural log of the limit, which would be equal to the limit of the natural log. And when you do that, you can bring the x down. Okay, just like kind of before, right? But this is still not helping us a lot. This is producing, this would be 0 times now the natural log of, let's see here, this would be 0 times infinity, right? Negative infinity. Okay, which isn't right yet, right? So we need to still maneuver it a bit. So we can write it like this. The next thing to try would be this, just to produce a ratio. So it'd be the natural log of sine x over 1 over x. Okay, and then this guy produces negative infinity over infinity. Right? So 1 over x is going to 0, this would be infinity, and this would also be infinity. Perfect. Negative infinity. Okay, so we can use L'Hopital's rule. Okay, so that means the natural log of y is equal to the limit as x approaches 0 from the right of the derivative of these two. Okay, so the derivative of the natural log of sine, that's going to be 1 over sine times the derivative of sine, which is cosine over sine. And so you're going to get a cotangent here in the top for this. And then this derivative is negative 1 over x squared. Okay. And so we can clean this up a little bit. Limit as x approaches 0 from the right of, now we'll put the negative x squared up top and then make this a tangent. All right, so cotangent is the same as 1 over tangent, and bring the x squared to the top. And so what happens here? Well, this is actually going to be 0 over 0 still. The limit as tangent goes to, as tangent and x goes to, x goes to 0 is 0, so this is 0 over 0. So we have to keep going, try, one more derivative. And so it should be noted here that these are all like, contingent upon the limit actually existing. And so we say the limit as x approaches 0 from the right of these guys. Now this one would become negative 2x when we differentiate it further. And the derivative of tangent is secant squared. And what do we get here? This is going to be equal to, let's see here, 0, right? Perfect. Okay, so that one we can get to. And so then what happens, right, because this will be going to believe 1, and then this goes to 0. So it'd be 0 over 1, so 0. Okay, so that means that the natural log of y is equal to 0. Okay, which, right, what does that mean? That implies that e to the ln of y is equal to e to the 0, which implies that y is equal to 1. Sorry about that. There you go. So y is equal to 1, right? So the original limit that we were interested in is sine of x raised to the x power as we approach that, as x approaches 0 from the right, and sort of through this process and using L'Hopital's rule twice, we were able to see that this is equal to 1. And this is the kind of thing that you hate to see, right? When you're a student, you're like, oh my goodness, how do I interpret this, right? But L'Hopital's rule gives us a very powerful technique that, when combined with like some good algebraic reasoning, can allow you to solve a whole range of very strange limits that are would otherwise elude us. So, all right, perfect. We'll end it here, and next time when we get together, we'll talk about improper integrals, right? So these are integrals. Think of a definite integral where one of the limits of integration is potentially infinite, right? So integrating over an infinite region is one aspect of an improper integral. So interesting stuff coming. All right, we will see you all then. Take care.